Welcome! Today, we'll be tackling LeetCode problem number 1037, valid boomerang. This problem challenges us to determine if 3 points in a 2D plane form a valid boomerang, that is, they must be distinct and non-collinear. Let's dive in and break it down step by step. In this problem, we are tasked with determining if 3 given points in a 2D plane form what is called a boomerang. A boomerang is defined as a set of 3 distinct points that do not lie on the same straight line. The input will be a list containing these 3 points, where each point is represented as a pair of integers, x, y, corresponding to its coordinates. Our goal is to return true if these points form a valid boomerang, or false if they are collinear. For example, consider the input 1, 1, 2, 3, 3, 2. These 3 points are distinct and not collinear, so the output is true. Now, let's look at another example to deepen our understanding. Take the input 1, 1, 2, 2, 3, 3. These points lie on the same straight line, which means they are collinear. As a result, they do not form a boomerang, and the output is false. On the other hand, if we consider a different input such as 0, 0, 1, 1, 2, 1, these points are distinct and do not lie on the same straight line, meaning they form a valid boomerang. Therefore, the output in this case would be true. To better understand the constraints and the approach to solving this problem, let's break it down further. First, the input will always consist of exactly 3 points, and each point will have precisely 2 integer coordinates, x and y, which range from 0 to 10⁻⁴. Additionally, all 3 points are guaranteed to be distinct. The key to solving this problem lies in determining whether these points are collinear. This can be achieved by checking the slopes of the lines formed between the points. If the slopes between any 2 pairs of points are equal, the points are collinear. Otherwise, they form a boomerang. To avoid complications like division by 0 when calculating slopes, we can use the cross-product formula. Specifically, the points x1, y1 is x2, y2, and x3, y3 are not collinear if the expression y2 y1 asterisk x3 x2 equals y3 y2 asterisk x2 x1 evaluates to true. This approach ensures numerical stability and simplicity. It's also important to consider edge cases, such as when all points lie on the same horizontal or vertical line, or on a diagonal line like 0, 0, 1, 1, 2, 2. In all these scenarios, the points are collinear, and the output should be false. By applying the cross-product formula to these cases, we can reliably determine whether the points form a valid boomerang. To solve the problem of determining whether 3 points form a valid boomerang, the key is to check if the points are distinct and not collinear. If they are collinear, they lie on a straight line and cannot form a triangle, which is what we need to confirm. One approach to tackle this is using slope comparison. The idea is to calculate the slopes between 2 pairs of points and check if they are equal. If the slopes are the same, the points are collinear, otherwise, they form a valid boomerang. However, this method has some drawbacks. First, there's a risk of division by 0 if 2 points have the same x-coordinate. Additionally, floating point precision errors can arise when comparing slopes, leading to inaccurate results. These limitations make this brute force approach less reliable in practice, even though it's conceptually straightforward. A more robust and efficient method leverages the concept of the cross-product to determine collinearity. Instead of comparing slopes, we calculate the cross-product of the vectors formed by the 3 points. This method avoids division entirely, eliminating the risk of division by 0 or floating point precision issues. The formula for the cross-product is straightforward: subtract the coordinates of the points to form vectors and compute the determinant of their components. If the cross-product equals 0, the area of the parallelogram formed by the vectors is 0, meaning the points are collinear. If not, the points form a valid boomerang. This approach not only avoids numerical issues but also ensures accuracy by relying solely on integer arithmetic, making it a more mathematically sound solution. Given the advantages of the cross-product method, we selected it as our strategy for solving this problem. The realization that slope comparison introduces unnecessary complications, such as division by 0 and precision errors, was a pivotal insight. The cross-product approach offers a clean, reliable alternative that directly addresses these issues. While slope comparison has the benefit of being intuitive and easy to visualize, its drawbacks in terms of robustness and efficiency make it less suitable. In contrast, the cross-product method is computationally efficient, avoids numerical pitfalls, and leverages integer arithmetic, making it both practical and elegant. The trade-off is that it requires a basic understanding of vector mathematics, but the benefits far outweigh this minor complexity. Analyzing the efficiency of our solution, the cross-product approach performs exceptionally well. The time complexity is 1, because we only compute a fixed number of arithmetic operations, regardless of the input. Similarly, the space complexity is 1, since no additional data structures are required. These characteristics make the solution optimal for this problem. In conclusion, the cross-product method is the ideal choice for determining the validity of a boomerang. It combines computational efficiency with mathematical accuracy, avoiding common pitfalls like division by zero and floating point errors. By using this method, we ensure that our solution is not only reliable but also simple and elegant, addressing the problem requirements in the most effective way possible. To determine if 3 points form a valid boomerang, we need to ensure two key conditions: the points must be distinct, and they must not be collinear. This guarantees that the points form a triangle and do not lie on a straight line. First, let's understand the input format. We are given three 2D points, each represented as a pair of integers, x1, y1, x2, y2, and x3, y3. The first step is to check that the points are distinct. This means no 2 points can be identical, as duplicate points cannot form a triangle. We achieve this by performing pairwise comparisons, checking if x1, y1 equals x2, y2, then comparing x1, y1 with x3, y3, and finally, x2, y2 with the x3, y3. Next, we need to ensure that the points are not collinear. To do this, we avoid calculating slopes directly, which can lead to precision issues when dividing. Instead, we use the cross-product approach, which is both precise and efficient. This method determines collinearity by working with integer arithmetic alone. The cross-product formula we use to check for collinearity is y2 y1 asterisk x3 x1 equals y3 y1 asterisk x2 x1. If this inequality holds, it means the points are not collinear, and they form a valid boomerang. Once we've verified both conditions, distinctness and non-collinearity, we can return true, indicating the points form a valid boomerang. Otherwise, we return false. There are two important insights to keep in mind. First, ensuring the points are distinct is a straightforward but essential prerequisite to forming a triangle. Second, the use of the cross-product is a clever way to avoid the inaccuracies of floating point division and potential issues like division by zero, making our algorithm robust and reliable. To optimize further, we can combine the distinctness check and collinearity check into a sequence of logical operations, minimizing any unnecessary overhead. The input representation for this problem is simple. The 3 points are given as tuples or arrays of integers, which makes accessing their coordinates efficient. During the cross-product calculation, we store intermediate values like differences, y2 y1, or x3 x1, temporarily, but no additional data structures are required. Let's break down the key operations. First, the equality checks for distinctness are performed in constant time, 1, since we are just comparing integers. Similarly, the cross-product calculation involves a few subtraction and multiplication operations, all of which also run in constant time. We must also account for potential edge cases. If 2 or all 3 points are identical, we immediately return false since a valid boomerang cannot form. Horizontal or vertical lines, which might seem special at first, are naturally handled by the cross-product formula. Additionally, the algorithm is well suited for points with negative coordinates because subtraction and multiplication work seamlessly with negative integers. Another edge case involves large coordinates. Thankfully, the problem's constraints ensure that the integers involved will not exceed manageable ranges, meaning we don't have to worry about overflow during calculations. Let's now consider the overall complexity of our solution. The time complexity is 1, because every operation, whether it's an equality check or a cross-product calculation, takes constant time. This makes the algorithm highly efficient. The space complexity is also 1, as we don't use any additional data structures apart from a few variables for intermediate calculations. Everything about this approach is designed to be simple, precise, and efficient, making it a robust solution for determining whether 3 points form a valid boomerang. This Python implementation determines whether 3 points in a 2D plane form a valid boomerang. A boomerang is valid if the 3 points are distinct and non-collinear. Explanation of the code. 1. Extract points. The method extracts the x and y coordinates of the 3 points provided in the points array for easy access. These are referred to as x1, y1, x2, y2, and x3, y3. 2. Check for distinctness. The first part of the code checks if any 2 points are identical. If 2 points are the same, the boomerang is invalid since the points are not distinct. This is done by comparing the coordinates of each pair of points. 3. Check for collinearity. To determine if the points are collinear, lie on the same straight line, we use the cross-product method, which avoids division and is numerically stable. The formula, y2 y1 asterisk x3 x1 equals y3 y1 asterisk x2 x1 ensures that the slopes between the points are not equal. If the slopes are different, the points form a triangle, making it a valid boomerang. 4. Return the result. The function returns true if the points are distinct and non-collinear, and false otherwise. Edge cases considered. Identical points. If any 2 points are the same, the function immediately returns false. Horizontal, vertical, or diagonal lines. The function accurately detects collinearity for all orientations. Overflow or precision issues. By avoiding division and using integer arithmetic, the implementation is robust against precision errors. This solution is efficient with O(1) time complexity since it involves a fixed number of arithmetic operations, regardless of the input values. The code is concise and directly addresses the problem requirements. This is the Java implementation of the valid boomerang problem. It mirrors the logic of the provided Python code, focusing on 2 main checks, ensuring all 3 points are distinct and verifying that the points are not collinear. The implementation leverages Java's array indexing and uses integer arithmetic to avoid precision issues. The class and method follow standard Java conventions for structure and naming. In this problem, we are tasked with determining if 3 points in a 2D plane form a valid boomerang. A valid boomerang means the points must be distinct and not collinear. The solution involves 2 key steps: first, verifying that all 3 points are distinct, and second, checking if the points are not collinear using a mathematical approach involving slopes. For instance, consider the input points 1, 1, 2, 3, 3, 2. We start by extracting the coordinates of the points. The first point is 1, 1, the second is 2, 3, and the third is 3, 2. This gives us the foundation for solving the problem by applying the 2 checks in the subsequent steps. The first check involves verifying that all 3 points are distinct. We compare the coordinates of each pair of points. The first point, 1, 1, is not equal to the second point, 2, 3. Similarly, 1, 1, is not equal to the third point, 3, 2. Finally, the second point, 2, 3, is not equal to the third point, 3, 2. Since no 2 points are identical, they pass the distinctness check. Next, we move on to the collinearity check, which uses the cross-product formula to compare the slopes between the points. For the given points, we calculate the differences in the x and y coordinates. y2 y1 equals 2, x3 x1 also equals 2, y3 y1 equals 1, and x2 x1 equals 1. Using these values, we compute the cross product. 2 times 2 equals 4, and 1 times 1 equals 1. Since 4 is not equal to 1, the points are not collinear. This means the 3 points form a valid boomerang. With both checks completed, we can determine the final output for this example. Since the points are distinct and not collinear, the result is true, indicating that these points do form a valid boomerang. Now let's consider a different example where the points might be collinear. For the input points, 1, 1, 2, 2, 3, 3, we again start by extracting the coordinates. The first point is 1, 1, the second point is 2, 2, and the third point is 3, 3. Moving on to the distinctness check, all 3 points are unique, so they pass this first condition. Next, we check if the points are collinear by substituting their coordinates into the cross-product formula. For these points, y2 y1 equals 1, x3 x1 equals 2, y3 y1 equals 2, and x2 x1 equals 1. Calculating the cross product, we find that 1 times 2 equals 2, and 2 times 1 also equals 2. Since these values are equal, the points are collinear. This means the 3 points do not form a valid boomerang. Therefore, the final output for this example is false. In our last example, we examine what happens when 2 points are identical. Given the input points, 1, 1, 1, 1, 2, 3, we first extract the coordinates. The first point is 1, 1, the second point is also 1, 1, and the third point is 2, 3. Checking for distinctness, we immediately see that the first and second points are identical. Since 2 of the points are not distinct, this example fails the distinctness check, and we can conclude that the points do not form a valid boomerang. The final output is false. To summarize, the solution is efficient because it avoids complex computations like division by relying on the cross-product formula for collinearity. This approach ensures numerical stability and quick evaluation of the conditions for a valid boomerang. To analyze the time complexity of this solution, we begin by looking at the input, which consists of 3 points represented as pairs of integers. The first step in the function is extracting the coordinates of these points using assignments like x1, y1 equals points, 0. Each of these assignments involves a simple lookup and assignment operation, both of which are constant time, or O1. Since we perform this operation 3 times, the total time for this step is still O1. Next, the function checks for duplicate points by comparing the coordinates of each pair of points. There are 3 such comparisons, each involving constant time equality checks. Therefore, this step also takes O1 time. So far, all operations have been constant time, contributing to an efficient implementation. The next step in the function involves checking for collinearity among the 3 points. This is achieved using the expression y2 y1 asterisk x3 x1 equals y3 y1 asterisk x2 x1, which computes the cross product of the vectors formed by the points. The use of the cross product ensures precision without the need for division, which avoids potential floating point errors. Each arithmetic operation, subtraction, multiplication, and the final comparison is performed in constant time, or O1. As a result, this step also has a time complexity of O1. Since all the steps in the function involve constant time operations, the overall time complexity of the solution is O1. Now, turning to space complexity, the input itself does not contribute to the algorithm's space usage since it is provided externally. Let's explore the memory usage in more detail. In terms of space complexity, the function uses a few local variables to store the coordinates of the points, x1, y1, x2, y2, x3, and y3. Each of these variables requires O1 space, and no additional data structures are created during the execution of the function. This means the total space usage is constant, or O1. Comparing this to a brute force or naive approach, we can see how the proposed solution is more efficient. A brute force method might involve calculating the slopes between all pairs of points explicitly using division to compute values like m1, m2, and m3, and then comparing them. This approach introduces additional computational overhead and the risk of precision issues with floating point arithmetic. Furthermore, handling undefined slopes, such as those caused by division by 0, would require additional logic, complicating the implementation. The proposed solution avoids these complications by using the cross-product method, which is both efficient and precise. When analyzing the best, average, and worst cases, we observe that the function performs the exact same set of operations regardless of the specific input values. This means that the time and space complexities remain constant, or O1, in all cases. To mathematically prove the big O complexity, we note that the function involves only a predefined sequence of constant time operations, such as coordinate extraction, equality checks, and arithmetic calculations. Since none of these depend on the size of the input, the time complexity is O1. Similarly, the space complexity is O1, because the function uses a fixed amount of memory, regardless of the input. In conclusion, this solution is optimal, achieving both time and space complexities of O1. One common mistake when solving the valid boomerang problem is failing to check if the points are distinct. If any 2 points are identical, they cannot form a triangle, which makes the boomerang invalid. To prevent this, ensure that all 3 points are unique before performing any calculations. Another frequent error is relying on floating point arithmetic to calculate slopes, such as using dy divided by dx. This approach can lead to precision issues, especially when comparing values. Instead, you can avoid division altogether by using the cross product or integer arithmetic, both of which are more reliable. Additionally, errors in computing the cross product itself can lead to incorrect results. A small mistake, such as a sign error in the determinant formula, can make you misjudge whether the points are collinear. To address this, carefully apply the formula x2 x1 times y3 y1 minus y2 y1 times x3 x1. Attention to detail in these calculations is crucial for accurate results. Neglecting edge cases is another common pitfall. For example, vertical or horizontal alignments can cause division by zero or incorrect slope calculations if not handled properly. The cross-product approach is particularly useful here, as it naturally accommodates these scenarios without requiring special treatment. Another issue arises when developers overlook input constraints. While the problem might specify certain bounds for point coordinates, custom test cases could violate these assumptions, leading to unpredictable behavior. To avoid this, always validate the inputs to ensure they conform to the constraints before proceeding with your solution. By addressing these common mistakes, you can make your implementation more robust and reliable. When it comes to interviews, the mathematical formulation of your solution is key. Interviewers often favor candidates who rely on simple, efficient mathematical techniques, such as the cross product, over approaches like slope comparison that are more prone to errors. Expect to discuss edge cases thoroughly, such as what happens with duplicate points or when the points form a straight line. Even though this problem is not computationally intensive, your ability to handle edge cases gracefully and avoid unnecessary complexity will leave a strong impression. Communication is also critical. Be prepared to clearly explain why your chosen approach is better, such as how the cross product avoids floating point precision issues. Finally, practicing related problems can help solidify your understanding. For instance, LeetCode problem 149 focuses on finding the maximum number of points on a line, which shares the concept of collinearity. Meanwhile, problem 336, though involving strings, is useful for honing your ability to handle edge cases effectively. Another related problem worth exploring is LeetCode 103, which involves binary tree zigzag level order traversal. While the context is different, both problems require a careful analysis of patterns, whether in tree traversal or collinearity. For a more advanced challenge, LeetCode 587, Erect the Fence, introduces the concept of convex hulls and builds on the understanding of cross products. When comparing alternative approaches, slope comparison might seem straightforward since it involves calculating the slopes between point pairs. However, it is prone to floating point precision issues and division by zero errors, making it less reliable. The cross-product method is preferred because it avoids these pitfalls and handles edge cases more robustly, though it may involve slightly more code. Another viable approach is calculating the area of the triangle formed by the points. While this is mathematically equivalent to the cross product, it may feel less intuitive for some candidates. Understanding the trade-offs between these methods will help you choose the best solution for the problem at hand. Great job! We've reviewed the valid boomerang problem and learned how to determine if 3 points are distinct and non-collinear. These concepts are crucial in geometry-related questions, so keep practicing. Thanks for watching, and don't forget to like and subscribe for more problem-solving content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!